we've got one more constraint to cover: cacheability. Caching isn't easy. It can dramatically increase performance, but it's also one of the first things to look at when unexplainable bugs seem to happen. HTTP cache is considered the holy grail of caching, so that's the one we're going to implement. We will first learn about the different cache types as defined by the HTTP cache standard. We'll have a look at Microsoft's response caching middleware, and we will learn how that compares to that HTTP cache standard. After that, we will learn about cache expiration and validation models and the cache control header. Let's dive in. The cacheable constraint states that every response should define itself as cacheable or not. So in a way, it is quite easy to adhere to this constraint. We can simply add a response header stating that the response is not cacheable. And that is a perfectly valid approach. But well, that would make this a very short module, so instead we're going to see how we can ensure that responses are cacheable. For this, we will use HTTP caching, which is part of the HTTP standard, which you're looking at right now, and described in full in RFC 7234. Now, I mentioned these two RFCs, but in fact, they are at this moment obsolete. In June 2022, a new HTTP caching RFC was released, RFC 9111. You're looking at that right now. That being said, June 2022 is, especially in terms of adoption, very early days. It will take years for all cache servers, providers, libraries, and so on to be fully updated to RFC 9111. So I figured it's worth mentioning both. That being said, the changes really aren't that impactful. You're looking at them right now in Appendix B of RFC 9111. The changes are mostly focused on clarifying what wasn't clear before. In any case, what you will learn in this and the next module applies to both the old and new versions. Let's have a look at what RFC 2616 stated as a bit of a mission statement on caching. It stated that caching would be useless if it did not significantly improve performance. The goal of caching is to eliminate the need to send requests in many cases and to eliminate the need to send full responses in many other cases. Eliminating the number of requests that have to be sent reduces the number of network round trips required for many operations. HTTP cache uses an expiration mechanism for that purpose. Eliminating the need to send full responses reduces network bandwidth requirements. For that, a validation mechanism is used. It does depend on where the cache lives on what exactly is reduced by a specific mechanism. We'll get to that. So, we will look into expiration and validation. But let's talk about that cache first, looking at it from an API point of view. We're working with HTTP, and the cache is a separate component. It sits between the client application, which is the consumer of the API that makes requests, and the API itself. This cache must accept requests from the consumer and pass them on to the API. It will also receive response messages from the API and store responses that are deemed cacheable. Those responses will potentially be forwarded to the consuming application. If the same response is requested again, the cache can send the cached response. So we can look at the cache as the middleman of the request-response communication between a consuming application and the API. Well, that's interesting, but it's also a bit confusing. This would mean that a request from a consumer still has to be sent to the server. Sure, a cached response can be served up from the cache, so we don't necessarily hit our API code anymore, but it is still a request and response that's sent over the wire. Well, the confusion comes from the fact that in HTTP cache, There's actually three different types of cache. Let's have a look at those. So, in HTTP, there are three cache types. One is the client cache or browser cache. It lives on the side of the client application. A browser is an HTTP client, but we can extrapolate that. If we're building, for example, a mobile client application, that client application, which communicates with the API through an HTTP client instance, can potentially have a private cache. It's called private because the resources are not shared with anyone else. They're kept on the client for each consuming instance. So, good examples are a cache on your mobile device, but also a cache in local storage for an Angular application. The second type is the gateway cache. This is a shared cache. The resources it caches are shared across different applications. This type of cache is used on the server side. Other names for this are reverse proxy caches or HTTP accelerators. This is thus the cache type that is often put in front of APIs. The third type is the proxy cache. It's also a shared cache, but it does not live at the consuming side nor at the side of your API. It lives on the network. They are often used by large corporations and ISPs or content delivery networks to serve to thousands of users. If you've ever had to change your browser settings and input a proxy address, well, you've used one of these. And probably, if you've surfed the internet a bit, you've used one of these without knowing it. Most of the time, combinations are used. A private cache at consuming side combined with a gateway cache server side and maybe a proxy in between. Depending on whether or not a response is cacheable and where it is allowed to be cached, we might hit our backend right up to the database. Or we might hit a proxy or gateway cache without having to communicate with our database. Or we might only hit a private client-side cache, eliminating communication between client and server completely. In the Microsoft world, for caching, the response caching middleware is sometimes used. Let's learn what that has to offer. So, to support caching, we essentially need two things. The first thing we need is a way to state, for each resource, whether or not it's cacheable. That is done via a response header. There are various headers to consider and we will look into those, but the one most often used is the cache control header. An example might be a cache control header with maximum age set to 120. This states that the response must only be cached for 120 seconds. To achieve that, the response cache attribute is used. But all that does is set the response header. That doesn't mean the response is actually cached. We still need a place where it can be cached, a cache store. As we just learned, there's different types of that, at client level, server level and proxy level. Microsoft provides a cache store we can add at level of our API by adding the response caching middleware to our request pipeline. The middleware is responsible for storing cacheable responses and serving them up from its store. Combining these two thus leads to what we need. Let's have a look at how to do that with a demo. In this demo, we will learn how to use the response cache attribute to control the cache control header on a response message. We're looking at the courses controller. Let's say we want to make a course cacheable. We can add the response cache attribute to the getCourseForAuthor action for that. Let's set the duration to 120 seconds. There's a few more properties we can set to control the cache. We will look into those later. For now, this should do the trick. Let's give this a try. Let's send a request to get a course. Here's that course. Let's have a look at the headers. And there we go, a cache control directive with a maximum age of 120 seconds meaning that this response can be cached for 2 minutes. Public refers to the location where it can be cached. A value of public means that this response can be cached by both shared and private caches. So at server level, proxy level or client level. If it would have a value of private, it can only be cached by private caches. What we want to do now is send this request again, but have it served up from a cache. So we shouldn't hit the get course for author action. Let's set a breakpoint there so we can check that. Before we send the request, we must check something. Let's open Postman's settings. There's a setting here, send no cache header. On my machine this is already set to off, but by default this is set to on. And we obviously don't want that, as that will result in a response not being served up from our cache. So make sure you set send no cache header to off, in case it is still enabled. And let's send that request again. And we still hit our breakpoint. Maybe we just waited too long. So let's continue and let's send this again. 120 seconds definitely haven't passed now. And we again hit our breakpoint. So even though the response of the previous request was cacheable for 2 minutes, it wasn't actually cached anywhere. We need a cache store for that. Let's add one in the next demo.